Friends, it's my pleasure to welcome you for the course on high voltage engineering. Myself, Ravindra Arora, and my colleague, Dr. Bharat Singh Rajpurohit, have together prepared it. We've also written a book which is there in the reference. You can always consult the book, which was published last year. I have earlier books, but the latest one is published together by both of us last year. First of all, I would like to apprise you about what is high voltage engineering. There are a lot of misconceptions about what is high voltage engineering. High voltage engineering is nothing but the investigation of the behavior of electrical insulation, dielectrics we also call it. How do they behave under different conditions of electric field? How do they behave under different conditions of pollution, or when there is some foreign particle in it, etc. Electrical insulations, you would be aware, the most widely used electrical insulation in the world is the atmospheric air, and that's the cheapest possible available. If you see the transmission lines, what is the insulation between you and the high voltage conductor? Is just nothing but the air. And then we have liquid insulation, liquid transformer oils, mineral oils. There are some other oils also there. Then we have solid insulation, that may be paper or plastic material or porcelain or glass or n number of solid insulation. And sometimes in an apparatus, there may be number of insulation systems or number of insulation which make the total insulation of the apparatus. And how do they behave, the insulation or the dielectrics under different voltage conditions, under different electrode configuration, that is electric field configuration, when they are affected by the atmosphere, etc. And that investigation and that knowledge is nothing but high voltage engineering. Obviously, when you produce an apparatus, you do want to test it, whether your insulation system provided to the apparatus is working all right or not. And that for testing the apparatus, we need high voltage laboratories, we need equipment with which we test the apparatus, measuring instruments, etc. And that is all done in high voltage laboratories. So that becomes the high voltage laboratory techniques are involved. We'll also cover about that. First of all, I would like to go to the next slide. The high voltage, I talked about the importance of high voltage. Then we need, why do we need higher voltage? You know that the power rating, W, real power, is nothing but V into I. If we consider the cos phi or the power factor to be ideally uniform, I would say ideally 1. So it is V into I. So if you want to increase the power rating of any apparatus or installation, what do we need to do? we cannot increase the magnitude of the current indefinitely. But we have, you can say, been able to increase the magnitude of the voltage practically indefinitely. Some 100 years back, or more than 100 years back, it was thought 110 kV will be the highest transmission voltage. But we do have today in the world 1150 kV transmission voltage. In the past 50 years, the leap power systems has taken place. It is not nothing but because of the high voltage availability, application, and that is how we are able to handle very large demand of power. We are able to generate the power, transmit the power, and bring it to the consumer by what we call it to be distribution. Let's mm, we'll be also talking about the voltage levels all over the world and the power consumption levels, etc. But let's talk about one very important aspect, and that is uh, the importance of high voltage insulation design and testing. I think I have talked about it. Uh, if you see the slide, the, the, as I just now mentioned, power generation, then the power has to be sometimes transmitted to long distances because the distance between the generating stations and the load need not be uh, um, very close. They are often very, very long. And then we need high, uh, we need larger machines to be installed when we have in the generating stations. Earlier, we used to have even 5 megawatt was considered to be a big machine, 5 and 10 megawatt. But today, 650 megawatt generators are being um, produced in our country. And the level of voltage at which this power is produced in the machine, that is synchronous generator, we call it, is at 22 kV only. Then uh, we would like to increase the voltage, but there are constraints in the machine to go for higher voltage. You can imagine when it is 650 megawatt at 22 kV, the magnitude of the current would be very, very large. We'll calculate it, okay? And then from 22 kV at the generating stations, the uh, the power is the voltage at which it is being generated, maybe 11 kV or 22 kV, is uh, enhanced. It is stepped up for transmission purpose, because for transmission at 22 kV, it is not advisable. We'll see how it is. May have a lot of losses because of current will be high, etc. So for transmission, we need higher voltages. And for transmission, as I mentioned, we have in the world gone to 1150 kV. In India, we have gone to 800 kV AC and plus minus 800 kV DC also. And but however, the distribution, when you can imagine the power is consumed only at 220 or 230 volts, and it has to be then stepped down and then distributed accordingly the power. So that distribution system is also very elaborate, very is in one way you can say very complicated, and so that you can provide the quality of power that is the voltage, and the main thing is there, the voltage and the frequency to the consumer at the designated level of 230 volts. Most of the loads in our country are single phase 230 volts supplied by 400, about 420 or 30 volts three phase systems. All the things together, that is generation, transmission, and distribution systems, they are interconnected. So to say, they are interconnected today in our country, throughout the country, from north to south, and from east to west. What do we call this interconnected power supply system? Power supply system, that means it is generation, transmission, and distribution, comprises of all the three, a power grid. So how would you define a power grid? In fact, when the distributed generation takes place, the generation of power is always distributed, because the sources of power, that is, you can say, you can classify also. So in the recent past, the coal was the main source of power. We have in India coal belts near Singrauli, for example, and there are a number of thermal power stations there. Then we have a lot of potential for hydroelectric in the Himalayan region, otherwise also. Then wherever the hydroelectric, you can say the waterhead is available, the hydroelectric plants are constructed. So the generating stations are distributed all over the country. The recent trend, I mean, not very recent, in the last 25 years, there's renewable sources of energy, that is the solar power and the wind power. They have been integrated also to the power grid. Solar power are available, the best place where the highest intensity of solar light is available, that is PV panels are installed, that is in Rajasthan and around. Wind power are installed near the coastal areas. So all these sources of power are distributed all throughout the country. And for example, solar power is available in the daytime. Then wind power may be available anytime. And hydropower, you can keep a reserve. If you don't run the turbine, the waterhead is there. And the thermal power stations, unfortunately, do not have that flexibility. They run continuously at a certain level of generation of the electrical power. So the best way to have economic conditions for the generation, distribution, and utilization is to have a power grid. In India, we have 5 regional grids. For example, the northern region, the northeastern region, eastern region, western region, and southern region. So 5 regional grids are there, and over the time, all these 5 regional grids have been interconnected. That has given rise to a national grid, and the dispatch center for the national grid is, of course, in the more where the power is handled more, that is near Delhi. So all the regional grids are in continuous touch with the national power grid, and that is how the power is controlled and brought to the user in its best quality. What is the advantage of power grid? The foremost advantage is that secured and reliable power supply. Secured and reliable power supply means when I've talked about this slide already. This is the typical sketch of the power grid. As you can see, the generating stations are connected with the help of transmission lines. All generating stations are connected to the one system, as you can see on this sketch, and these form a power grid. So how can you define the power grid? As you see in this diagram, you can define the power grid with a very simple definition, that is interconnected generating stations make it a grid. A power grid is nothing but an interconnection of all power generating stations. And as I mentioned, some of the generating stations may have generation at 11 kV, some maybe at 22 kV, then they are stepped up with a transmission line at 220 kV or 400 kV or 800 kV AC. They also the transmission line may also have voltages like plus minus, or only monopolar DC or bipolar DC, plus minus 800, plus minus 500 we have in our country, and that is how they are interconnected, and the power is brought near to the load centers. The load centers are in the big cities. The biggest load center in the country is nothing but the National Capital Region, and all cosmopolitan cities like Bombay, Calcutta, Bangalore, Hyderabad, they also consume very large amount of power, but the generation takes place at far distance, and with the help of the power grid, the power is brought there. Yeah, let's come back to the advantage of power. Suppose there is some fault in one of the power generating stations. Under this condition, the power can be diverted from other generating stations to the load near to the generating station, which might have been taken out of the circuit because of the fault conditions. So you can say diversion of power. Diversion of power is also important. For example, in the evening hours, solar power is not available. So we can keep the hydroelectric power as the water head in reserve, and put on the hydroelectric plants when the other source of power is not available, for example, the solar power or wind power, etc. So we can divert the power suitably and also economically. So that is one big advantage of the big advantage of I think I've talked about it, the 5 national grid, etc., as you can read it. Then secured and reliable power supply, as I was talking about. Then you may be aware, everything in the world needs maintenance. Let it be the human body or any gadget, everything needs maintenance. And so every power plant needs some maintenance. And when the maintenance work, sometimes the scheduled maintenance work is taken up, we may have to shut down the power plant. Under that means it is not able to supply the power to the grid. Under this condition, what happens? Again, the power to the grid is supplied by the other generating stations, and the power is not interrupted to any consumer. Now, when we have very large grid, that means when the total power generating capacity of the total grid is very large, the magnitude of the reserve capacity needed would be much smaller compared to if we had proportionately the magnitude of the reserve capacity which is used when some plant is under maintenance or some plant is out of service would be larger proportionately for a smaller system as compared to the larger system. And the grid has advantage of having a very large power handling system. So the percentage wise, the reserve capacity required for meeting the unforeseen situation or even the scheduled maintenance situation becomes much smaller. Well, that is a big saving in the cost of supplying the power. And again, it is said the ability to install larger unit size, the size of a single unit supplying power is in practical sense, it is said that between 5 to 10% of the total power handling capability of the system. Now, when we have power grid, the total power handling capability is very, very large. In that case, we can install larger single unit sizes, and the larger is the unit size, more economical is the power generation. For example, if you generate power with three 200 megawatt generators and with one 650 megawatt generator, total capacity is the same, 3 times 200 and 650 megawatt single unit. The power generation by the single unit of 650 megawatt would work out to be much economical. So it is desirable to install larger unit sizes, but the larger unit size, if it goes out of the circuit, the whole system gets such a jolt that it may not be able to withstand with the supply of power to the consumer. But when the total handling capability of the grid increases, we can also install larger unit. And that is why the single largest unit should be something between 5 to 10% of the total power handling capability of the system. So that also increases. Another very important thing in power supply is, you must have noticed sometimes that in the evening hours, the voltage goes down. Why does it go down? Because in the evening hours, the load to the total system increases considerably. And when the load increases, the generating capability has to be increased too. And when it lacks, that means the load is increasing and the generating capacity is not increasing, the power supply quality, that is one thing, voltage and frequency also goes down. Under that condition, it would be advisable to have some to start generation of power through different sources under the peak load conditions. And there we take help with the hydroelectric power plants, where the hydroelectric plants take, because the hydroelectric plants take only 3 minutes, 3 to 4 minutes maybe, when we open the gates, start running the turbine and synchronize it to the grid. That takes such a short time, unlike the thermal power stations, which take hours and hours, 10 to 12 hours minimum, because you have to have the rated temperature of the steam, superheated steam, etc., and that takes very long time. So now, to meet the peak load, which rises very quickly in the evening hours, when the best solution is to start new hydro generating plants and synchronize them to the grid. And this process, because it takes very less time, the peak load is best met with the hydroelectric plants. And hydroelectric plants, you can imagine, as I mentioned, they are located far away from the load, wherever the hydroelectric potential is available. This is how the grid system again helps in meeting the peak load quickly with the help of diversion of power, starting new generating power plants, etc. So that is another very important advantage of the grid power grid system. So as I mentioned, we have the national power grid, which is taking care to bring power of the best possible quality to you all throughout 365 days a year and from years to years. I was mentioning what is the need, as you can see in this slide, what is the need for high voltage in power systems. As you can see, three-phase power, you must have learned in the power system courses that three-phase power is given by a very simple equation, √3 V line I line cos phi. The line-to-line voltage, line current, and the cos phi. If you take, for the sake of quick solution, let's take the cos phi, that is the power factor, ideal power factor, let's say 1. This is not practical, but it may be ideal. Okay, so in that case, the power when you calculate becomes three-phase power. You can calculate V square or V line square by ZC cos phi, and cos phi taking 1. Another very important thing, the impedance, as you see on this slide, impedance has been taken to be between 250 and 350 ohms. That is the characteristic impedance of the transmission line. You can see the characteristic impedance of the transmission lines varies between 250 to 350 ohms for the majority of the transmission lines. And when we come to this equation, the three-phase power is equal to V line square divided by ZC, and cos phi is 1. The power is proportional to the square of the line to line voltage, V line. That means if you power handling capability is proportional to the square of the voltage. If you want to increase the power handled by a transmission line and increase the voltage, the power handling capability will increase tremendously. So it is not desirable to increase the current, line current, because the I square R losses, that is the which get converted to heat in the conductor, are not desirable. And there's a power loss also, a tremendous power loss. The transmission lines have got a very high efficiency. If we had increased the current instead of voltage, you can imagine I square R loss is the real power loss. So the efficiency of the transmission lines would have gone down like anything. So it is not desirable to have to increase the current, but if we increase the voltage, we can increase the power handling capability of any three-phase system. And this is true with not just transmission line. This is true with all electrical installations and gadgets like generators, like transformers, etc. So to be able to handle larger amount of power, the voltage, higher voltage is required. That must be taken care of. Yeah, the equipment efficiency slide is there. You can see the large generators have got a efficiency to the order of 95%. Electrical, I'm talking about the electrical efficiency. I'm not talking about the thermal or the energy conversion efficiency, only electrical efficiency. Then sometimes you might have heard that the power supply system is having tremendous losses, and those losses are actually not the electrical losses, but the power theft, which unfortunately are clubbed with the power system efficiency. And in our country, unfortunately, power theft is not a new thing, it's a very common thing. And that must be checked, and that should not be included in the electrical installation efficiencies. That is a wrong interpretation of the hard work done by the electrical engineers, I would say. Yeah, of course, as I just mentioned, the efficiency of the fossil fuel and thermal power generating stations it used to be around 30%. It has been increased to 40% gradually, and the efficiency of hydropower stations is obviously much more, because there are not much losses there. But even the transformers have got very high efficiency. Motors, transformers, generators to the tune of 95%. Yeah, the level of voltages. As you can see, people have classified low voltage, medium voltage, high voltage. High voltage is classified between 115 to 220 kV. Extra high voltage, 345, 400 and 500 kV. And ultra high voltage, 765, 1100 and 1200 level, 1150 or 1200 kV level. But I simply do not agree with this classification. In fact, you must have known and read near your house or near your nearest substation, danger, 440 volts. Danger, high voltage, 440 volts. Even the 440 volts three-phase system is dangerous and considered to be high voltage. So everything is high voltage, and classifying this, the range, medium, high, and extra, and all, this is very confusing, and this is not followed uniformly all over the world. So it would be advisable to mention the level of voltage, and everything is high voltage, instead classifying it extra and ultra, etc. So this classification is unwarranted, for I would call it to be, and because even 440 volt is considered to be high voltage and equally dangerous to the living being. Then let's go to the next slide. Yeah, rated voltages and frequencies in power system. In the consumer voltage level, we can we know the single phase consumer voltage level is 230 volts, as I was mentioning. But in some countries like the United States and Japan, they have taken they have designed their system to have the consumer voltage level, single phase consumer voltage level, at 120 volts only. The only advantage, what I consider, for having 120, not 230 volts, is the safety of the voltage. And with the modern gadgets and tripping devices, even 230 volts is as safe as 120. And this single phase voltage is always between a phase and the neutral voltage. This is not line to line voltage. Line to line voltage will be multiplied by √3. That will work out to be about 410, 20 volts. So the system is also called 440 volt system, and the system single phase voltage is 230 volts between line and the neutral. There have been in the distribution systems, as you can read, the 230 volt three-phase system in the United States or Japan, 400 volt or 410 volt distribution, three-phase distribution system in our country, or in most of the countries in the world. They follow the consumer voltage to single phase consumer voltage to 230 volts. Then earlier, the power was distributed at 3.3, 6.6, and also at 11 kV level. And these voltage levels slowly have been phased out, because you can imagine the power handling capability depends upon the total, the power handling capability depends upon the is proportional to the square of the voltage. So 3.3 kV system and 11 kV or 6.6 kV system would handle very less amount of power, and the load is continuously increasing. So 11 kV is one of the standard of the power distribution level, and then 33 kV, and also you can say 33 kV is also a distribution level, and which can also transmit the power to short distances. We have another standard system of high voltage distribution of power, you can say, adopted by the railways practically all over the world. It is being adopted at 25 kV single phase AC voltage. And in the electric traction system, you might have observed while traveling with the train that every 40 kilometers there is a substation which supplies the power to all the locomotives in that range of 40 kilometers, 20 kilometers on either side of the substation. This substation actually converts two-phase 132 kV into single phase 25 kV system. So the transformers installed at these substations of electric traction are actually two-phase 132 kV step down to single phase 25 kV system, because the traction locomotive gets the power at single phase. This leads to kind of an unbalanced system of distribution. You might have also observed when you travel with electrified train, electrified track, you can say, that there is a same dimension transmission line which also runs along with you on either side of the track, and that is nothing but three-phase 132 kV line, which is laid specifically to supply power to the electric traction system. Yeah. Now we did talk about initially the system of generation level, the rated voltages at the generation level. Three-phase generators are, you may have three-phase 440 volt generator, 3.3 kV, 6.6 kV. These are all small generators. When we go to the large generators, that is 110 and 220 megawatt power generation. One thing, the generators what we are talking about are nothing but synchronous machines, synchronous generators. Synchronous machine, as we understand, is we have been understanding, the things are changing. Synchronous machines have one synchronous speed, and the synchronous machine can be used either as a generator or as a motor. So such synchronous machines which have total power rating up to the tune of 110 to 220 megawatt generate power at 11 kV, whereas when we go to the larger generator, as I said, are desirable. 500 and 650 megawatt generators, the power is generated at 21.5, you can say 22 at 22 kV level. And still larger, but rare, 1000 megawatt generators have their rated power to the tune, rated power generation voltage level to the tune of 33 kV. That is, it is difficult to have to provide insulation within the windings of the generator for higher voltages, and that limits the voltage level at which the power is generated in the power generating machines or synchronous generators. Then, as I was mentioning, uh, from 11 kV to 440 volts or 33 kV to 11 kV and 66 kV to 33 kV are the steps at which the power distribution takes place. And ultimately, the consumption is either three phase 400 volts or single phase 230 volt. Yeah, you would wonder why these are multiple of 11. 11, 33, or even that is why we have been calling it to be 440 volts and not necessarily 400 volts. So multiple of 11, 66, 33, uh, and also we have been talking about 220 volts, 110 volts, 220 kV, 110 kV, etc. Multiple of 33 kV. In fact, the multiple of 33 kV is the system initiated by the British, and we have also followed that system in our country. But you would be surprised to know, for example, in Germany, the system is 400 volt, that is not 440 volt, 400 volt, 3 kV, 6 kV instead of 6.6 or 3.3 kV, etc. As you can see. So I'm multiple of 10, not multiple of 11. So this question I've been asked very often, that why this multiple of 11 is considered to be standard in our country, but it is not that it must be followed all throughout. Okay, for today, let's close our meeting. I'll be seeing you tomorrow with some new contents. Okay, thank you very much.